never know, It's like a frozen
I'm
picture.
purely theoretical.
In principle, you're here, but or you could be in more than one place, right? If you believe in quantum mechanics, it could be, it's a little bit of that. What's omniscience?
You haven't measured my presence yet.
But we don't have to worry about dead cats, right? So
I hope not. Yeah.
I mean, I've heard of the dead cat balance, but no, okay. That's not a very good metaphor. Okay, so let's see. Where were we last time? So I was moving all over the place, and I get it. People don't like it. They like linearity in their notes, and I'm sorry. It just occurred to me the reason I bounce around is because that's how I learn. I have to keep recycling, going back to something I had before, and I can't do it in a left to right fashion. And of course, I have all sorts of excuses for such crappy teaching. I say, well, the river of truth is not always straight. What does that mean? Show me a river that's straight. So anyhow, where were we last time? That's what we'll be talking about.
Expectations.
Please, can you say that again?
Expectations.
Expectations, and we, as you would expect. Sorry, we didn't do very much. Chuck, check your no. It was Chuck your YER luck, I think. Unless I misread it.
Yeah, we did an example with the dice rolling and the number of times you get your number that you picked.
Right.
Let's see here. And we did the one with a certain number of people in different buses.
Right.
Question of
that was pretty subtle, right? That was subtle because the difference between the average number of people in a bus and the expected number for this individual, from his point of view or her point of view, was slightly different, just a little bit different. It wasn't dramatic. So that was an interesting problem from that standpoint. You might not have noticed it if you just did a rough approximation. So what do we... how are the tests going along? I mean, what the triplicate problem and stuff? Are you? I don't want the answer. I don't want you to necessarily say you did it or not. But do you feel like you're making progress on these things? Or okay, that looks like a yes, a pretty emphatic yes. Okay.
Took some research, but I think we got it.
Good. Because I can't help but to. Listen, I can't. I just can't help myself. Given problems, in the past on triplicate, and a lot of times that if they're checked, the tutor will say, "Well, we'll just look at the book and do what the book did." So just to get warmed up here. Not everybody's here today. We're here. Let's have some fun. So, what do you think the check tutor does when they pop out a triplicate problem? What do you think they do? They look at the book, right? And when they look at the book, what do they do? What do they see that leads to their solution? Do you guys have you looked at that part of the book? What they do is they approximate the problem with a binomial setting. So your trials. You remember a binomial distribution has trials, right? So your trials would be, for instance, if you're doing a triplicate, you would have this many trials. So those are your trials. It's not n, it's n choose 3. And what is if you're doing the traditional triplicate problem, birthday type triplicate problem, what is the probability that any given 3 people have the same birthdays? Anybody know what that is? What's your P in this case? What's your success probability? Okay, I see it. I see it chat. Somebody may have it there. Check your luck. Okay, let's go over this again. A binomial distribution, you've probably already done this, the the Roy and Slim problem, right? So you've gone through that. You understand how binomial works. So it requires these independent Bernoulli trials, the independent trials, and each trial has the same probability of success. Okay, this is the standard binomial thing. So what is the success probability? So if you just have two people, what's the chance that they have the same birthday? Assume 3 to 65 possible birthdays. You got two. What is the what is the logic behind the answer to? So you got two people. What's the chance that they have the same birthday?
That's 1 in 365.
Right.
So-
Amy, you knew that, right? Or you did? Okay. You knew? Did you know that?
Yeah, I'm here. Don't worry.
Oh, I know you're here. I just wanted to know if you knew that.
I got my COVID shot, and my voice
Oh wow.
I'm sick
You're
because
talking about your second. You talked about your second shot.
second shot.
And let me guess. Moderna gives you the worst side effects. Was it Moderna?
Not Pfizer, but it's just it means my immune system's working.
Okay,
But
I'm not going to ride you. I'm going to give you.
Okay,
I'm going
thank
to
you.
stop asking. I'm going to stop asking you things.
I'm here though.
Yes, and I'm. You know what? I have to say that's really determination. If you're not feeling, you obviously have flu-like symptoms, and you're still here. So now I don't. Now I'm scared to take my second Pfizer. If I do, I'll be sadder but wiser. No, so never mind. But anyhow, so okay, Ethan, you now have to. You have to step in. So you're right. So if you have three people, well, first of all, what's the logic behind two people? The probability 1 over 365. Well, the first guy is going to be one of those days at random, right? Maybe he's on the third day of the year. Now, the second guy, what's his chance of having exactly that same birthday? Well, he's equally likely to be any of 3 to 65. So it's 1 over 365 that he's the same. Now, the same logic goes for 3. So the success probability is 1 over 365 squared. Okay, now I find this very amusing. Okay, as I've been a teacher for a long time, and I guess whatever math I've done, I now understand that there's a problem with our textbook. Okay, now this shows up in the check. They say, well, in our textbook, they say, well, we got success probability, we have the trials. We will approximate the binomial with a Poisson distribution. Okay, that's what I get. Okay, in answers from people that just take off the check or something like that. They take whatever is given. There's a logical problem here. If you're going to use the binomial approximation and then use the Poisson approximation, why the hell don't you just stick with the binomial? The more approximations you do, the less accurate your answer becomes. Why don't you just use the binomial? And of course, stupid me, I did that, and found out I got the same answer as the book. So just don't do any approximations on my test. Don't do that. Don't. I can't give credit for that now that I've warned you guys. It's really dumb to whatever the problem is. To approximate with a binomial and then approximate that with a Poisson. Okay, so I don't know how this happened. It's probably because when you're a book reviewer, I don't care how many editions this is. When you're a book reviewer, you tend to shy away from the really long, hard examples. You just look at the easy stuff. How is the book doing? I don't think anybody's read this part on the triplicate in his book. Okay, you could just go ahead and use. It turns out that these trials are not independent. They're not. This is whether 3 people have. I mean, it's already an approximation, but that's all I want to say about this. Just don't do it. Do the probability exactly. Do it exactly. Don't just write down what the Czech people are saying. I can't give credit for that.
I actually saw this part in the book where he talked about I think he said it's called Poisson approximation.
Yeah.
So what I did was, I mean, I don't know if I'm allowed to say, but I basically used it. I got a number, and then based on this number, I actually tried it, doing the probability.
Right, the hardcore, doing it.
Yeah, the hardcore one, and then I got
yes.
close to it. So
Yes.
then I used, just
Well, I think
assumptions.
that's fine. That's fine. I actually recommended you guys do that, but you don't need to go Poisson. You just a simple. You have to calculate the probability of no triplicate. That's no successes. That's really easy. That's 1 minus p to the n. It's just. I don't know. It's just this is a huge frustration to me because it looked so neat when it was in the book, and then I realized there's nothing in there, zero content. If you do the approximation, you get around 84. This is not a paradox. That's a lot of people. You're going to need 84 people for the probability. This is approximation that's gotten in the book for the probability of a collision, of a triplicate collision, to be bigger than 50%. This is their conclusion. So there's no paradox here. This is a big number. What the actual number is, we don't know, right? That requires some combinatorics. Okay, that's what we teach in the class. Somebody said Poisson equation, the Poisson random variable. We'll talk about it next time. It's just another random variable. We've done so far. We did binomial. We'll do Poisson. We'll do geometric, hypergeometric, negative binomial. We'll do these. We'll cover these things. They're just different random variables. But for now, I've got to do my regular stuff. Okay. So let me get started with that. I just thought I'd tell you this on the test. Don't turn in this nonsense. You've got to calculate the probability exactly. I mean, this puts you in the right ballpark, perhaps, but it's not. It's an approximation, and not only that. When somebody has an approximation in math, they have to tell you what the margin of error is. And again, we've been over this. If I tell you I have $10 in my bank account plus or minus $1 million, that $10 is an approximation. But it's since if I didn't tell you plus or minus $1 million, it means nothing. Whenever there's something approximated, you have to have a bound on the error. That's critical. Otherwise, there's zero content. All right. Okay. So where was I last time? I'm going to have to use notes today because I'm burned out from the previous hour. Okay. So what was the definition of variance? Var(x)? Okay. So that's E. It's an expectation of what? X minus mu squared. And this is sort of the critical thing here, even though it's partly washed out. But variance is an expectation, and it's sort of a strange thing. It's the square of you're computing here the difference is squared between x and its mean. And you might say,
I forgot we did that.
Yeah, well, this idea of squaring distances and adding them up, that comes from the least squares. I mean, it's also part of the least squares, right? Regression, which you may have learned in AP stats or something like that. But
It's like distance formula, right?
No, distance would be this. Okay, so that was the alternative. If it's distance, I think it would be like just this. I mean, that would be a measure, right, of the dispersion of your data. Okay, but they don't use that because of problems with analysis.
So, trying to understand. So, what's mu? I
That's
forget.
mean. Mu is, instead of having to write this again,
Oh, okay.
it's just a quick, it's the mean. The mean is not enough. We were talking about this before, for those people, and there's a few that are going the stat route. If you just talk about the mean, you're losing another major aspect of how your data are distributed. Okay, yes, the mean is the average. In the add up all the values and divide by the number of them. But you're missing the distribution. I'm sure we talked about this before. You could have one normal curve that looks like this, and you can have another one that's Gothic, which looks like a wave. I've lost my ability to draw the normal curve. So this is like much less. You measure it from the center to the break point on a normal curve, where the inflection changes. So this one is much less dispersed than this, okay? And you need a measure of this. And the measure is the square root of the variance. And that's they give a name for that as sigma. So I'm just giving you a little
Standard
bit.
deviation, right?
Yeah, and so it's the break. It turns out it's the break point. So this distance here, I probably can't see it, but that's sigma. Sigma from here to here, and here the sigma is supposed
It's
to.
funny. I never knew that. Like I knew all about standard deviation and stuff, except I didn't know that. I didn't know that it was the inflection point. I just knew it was like a an idea of like most of your values fall into here. I thought it was just totally arbitrary.
Well, it is true that most fall into this. It turns out that 68% of your data do fall in they're within one standard deviation of the mean. It's true. And,
Right.
but I talked to a real statistician once and said, I forget about all the math. You tell me what the standard deviation is. I wanted to know. And she said to me, forget the math, forget everything, forget the inflection point, everything. She said, if you put your data in a hat and you picked out one of the numbers, on the average, you would be that far away from. It's a typical, not average. Typical is a median. You're typically that far away from the mean.
Oh,
Okay,
so it's
so-
like the average of how error of what the
Yeah,
error is, basically.
Maybe,
Kinda.
but you've got to be careful with average. Average is associated with mean. I think when she said typical, she was going more towards median.
Oh, I see.
Different concept, but okay.
Normal.
Let's do something with
Load.
this stuff.
Yeah, median.
So let's do something here. So we're supposed to do all the books. They say, well, let's multiply this out. Minus 2x mu plus mu squared. Let's just multiply it out, okay? And then I've told you, but have not proven, is that the expectation is linear, okay? It's like a linear operator, so it can move in. What you can do is move this expectation in through here. So let me use a different color so that it stays in your mind. That this is the ax plus b. This is one of the classic properties of expectation. This is a, b, x plus b. And it's also the fact that this is a classic. This is a consequence of the general formula that this guy is. These are different values of so g of xi, p of xi. So this actually is a general. This is a consequence of this. This is proposition 4.1 in our book.
So I'm getting really confused about notation. So what does the brackets mean? What anyway? Like
Okay, well, this is a definition. Okay, so I think when you mean the brackets, you're saying what is g of x? What does this mean?
yeah.
Okay, that has a definition. We are in discrete random variables, so there's no integral here. It's a discrete random variable, and what it is, by definition, is you look at all of the countable number of values that x can take on. This is a function on the sample space. Okay. Okay, it's a misnomer to call it a variable, but it's been called that since day one for the field. So anyhow, what you will do is you take the different values.
What did you just call it though? It's a
Random variable.
function on the sample space.
Yes.
Okay.
For instance, if your sample space, the outcome of the experiment is you roll two dice, right? So you get these two numbers, a die one and die two, right? It could be that the function you want that you're concerned about is the sum of those. You don't care how that sum occurred, whether it's 2, 3, 3, 2, whatever, 1, 4. You just want to know the sum. So that's what you're concerned with. So this is why you have this is why you say you have these functions. Okay, the sample space may not involve numbers, right? I mean, it could be birth orders or something like anything, but the random variables are functions on the sample space.
Okay.
But I want you to know this this formula. It's very critical, and we did a couple of these last time. But this is the expectation will be the different values you have times the probability of those values occurring. Okay. Okay, I'm not trying to put you off. I definitely want to make sure you have this solid. But my goal was to give you a solid example. If X was the result of a die roll outcome, result. Let's put a result. Sounds more like numerical, right? Then what would E of X be? We did this like twice, but I want to make sure you have this. Do you remember how we calculated this? We took the result. What are the results of a die roll? It's 1 through 6, right? We good with that?
Yeah.
And then you multiply by, each one has the same probability. So what's the result? The result is 7 halves. Okay.
Okay.
It's okay. I think you might have missed one, but it's good because I want to expand on this in a second. But if you have these results about linearity of the expected value, then what can happen here? So let's I'll try to prove this today, but right now I just want to talk about the variance a little bit. So
Yeah. What does that mean exactly then? If it's the expectation of that?
well, this is okay. This is the way you can think of this as another random variable.
Random function. Yeah.
Well, I know, but they use. If you say random function, nobody will know what you're talking. It's just the in math, certain terms get used over and over again, but it's the same term being used, but it's a totally different application. Like the word regular occurs about 5 million times in mathematics, and every time it's used in a different field or subject,
Oh yeah, I hate
it
that.
means something different, and sometimes it means
Absolutely hate it.
irregular, not regular. So yeah, but this is something that cannot be changed. It's okay. So this is, imagine that is your random variable. Anyhow, the E has the property that it can be distributed through here. Minus 2 mu. Remember, by the linearity, I'm assuming I have the linearity available to me. So what would this be equal to? Okay, so you look at this, and well, E of X squared is going to be what it's going to be. But this guy right here is mu. So this is 2 mu squared plus minus 2 mu squared plus mu squared. So what's that equal to? So when you're doing maybe on my final or something, you have to compute a variance. Okay, I've got to put something in there. Sometimes it's much simpler to just go into this, or maybe this has been given to you, to do this than to go back to the definition. Okay, I mean this is nuts and bolts kind of probability. You have to have this when you take the final. So let me expand on this die result here. So suppose that X was the die result. Okay, so let's see. Let's evaluate the variance, okay, according to this formula. So what would we have to do here? So tell me what we need to do. We need E. I don't know if you can see this. I'm running kind of small because I've got it. This is a long line. Minus, now what would mu squared be? Remember, we're rolling a die and we're investigating the variance. Do you expect the variance to be small or large? I mean, remember, it could be anything from 1 to 6, right? It's not like it tapers off at the edges. It's pretty much, it's sort of uniform, right? So we expect the variance to be something here. In fact, tell me what you think the variance would be. The square root of it has to be the average. 1, 2, 3, 4, 5, 6 has to be the average. Think of it as a distance from the mean. So, the variance is going to be something. Something. If you pull a 1 through 6 out of the hat, or the variance, it's.
What did you just say about average distance from the mean?
Well,
did you say the variance is going to be that?
The variance is the square root of the variance would be the average, the typical distance from the mean when you pull one of these outcomes randomly out. So the mean we know is what? We just calculated 7 halves, right? It's 7 halves. So the variance is somewhere around there, okay? It's somewhere, it's going to be something. It's not going to be right on top of this. There'll be typically, how far away are you from the mean? Well, let's calculate it. So what is mu squared? Let's see if you guys are following me. What is mu squared? What's E of X quantity squared? Okay, remember X is the roll in one die. Go ahead.
Oh, you mean, okay. So that would be 49 fourths, right?
Good. Okay. So we know that. Now, how am I going to evaluate this thing right here? Okay, so that's going to be what?
So you're going to take all of the actual values and square them, and then
Yeah,
get the expected back.
exactly. So the values will be squared. Again, we're using proposition 4.1 for those that are math major. I've got a few math majors in my class also, which I didn't prove, but we're doing that. So anyhow, let's calculate that. So we get 1 squared, which is 1 with what probability? 1/6, right? Now, what's the next one up? You get, what would the next one be? Remember, we're squaring the result. So the result, if you see a 2.
So 2, so 4 is the next result.
Right. And you might say this is a total terrible waste of time for me to do this, but you know what? It comes up in problems, more serious problems later on in the book that we'll do. And then what's the next one? 9?
9 for a roll of 3, and 16, and 25, and 36.
And plus 36 times 1/6. So let's guess. Take a guess on what you think. So sort of on the average, if you could square root what the average distance was, what do you think? I mean,
I would expect like 2.
or something, somewhere around that, maybe between 1 and 2. Okay, so let's remember we have to subtract off 49/4. Now this is sort of a calculation I got to do here. So I would take 1/6. Now I'm going to do this in my head because the numbers come out very nicely. That's 5, 14, 30, 55, 91. So we've got that, and then you have minus 49/4. This would be very embarrassing if it doesn't work out, right? So, sorry. Okay, so I already made the first mistake. This is 91 here, not 91/6.
Oh. Really?
Right? Okay.
Oh, yeah.
So let's see. How should I write this? What's the common denominator? It's 12, right? So 182 minus, what's 3 times 49? 147.
147.
Over 12. And what is that numerator there? Again, I'm only doing this because this occurs later.
I feel like that's 35.
Yeah, it's 35. 35. So it's 35.
I did it fast.
That's the answer. That's the answer. My notes don't have it because I did it before. But anyhow, that's the answer.
Cool. So that's almost 3, isn't it?
Right, you're right. So it's more than 2. Can you imagine that? So typically, of course, I have to take a square root somewhere, but they're going to jump around a lot because
I think it's because they're so spread out.
These are all. It's more than being spread out. It's that they all have the same weight. These numbers, you know what I mean? Because if you think of like a bell-shaped curve, if your data look like this, then if you're out here, you don't. Those are sort of rare observations, right? I mean, that or more extreme than that is sort of rare, right? Most of the observations cluster around the center. But when you have a box distribution or a uniform distribution like that, anywhere can show up, So it's an interesting thing, And when we do the continuous, then you're going to have to use an integral or something to figure out what the variance is.
Yeah, that's really interesting. The inflection points or whatever, the standard. No, wait, that's the variance. The standard deviation is the square root of that, right?
No, where this inflection point is at, that is, if this is a standard normal, right?
No, I mean what we just computed is the variance, right?
The variance, right? But it's not normally distributed. It's okay.
I know that it's not normally distributed, but if we were to approximate it with a normal distribution, that's what I'm thinking about.
Well, you can't. It's okay. You can't approximate. I mean,
but it does have a standard deviation, right? I mean, we can just.
Yeah, but normally, okay. So what we're dealing with, if it's continuous, is a distribution that looks, and the continuous version of it will be something like that. Very unnormal in its shape, right?
Yeah. Well, I know that.
Yeah, that's really. But
I was just thinking, like, whenever I did, science class and from when we first learned this to like everything I ever did in science classes is like compute the standard deviation. And like, even if it doesn't have a normal distribution, we would approximate it as having like a normal
Okay,
distribution to get an
that's
idea
okay.
of it.
Okay, yeah, but that's something we covered at the end of the class. This is an interesting point. You talk about the central limit theorem. So if you take a sample of size n and you take its average, you're looking at the sampling distribution for the mean, and that is approximately normal. Okay, so that's different than this, but it's you take in a sample. So if this was my distribution, I take a sample in here of say 4 things, I average them, I get some number that's close to the center. So the sampling distribution then would have a normal shape to it, but that's different. But okay, let's.
Yeah, well, I think of everything in terms of like random samples, basically, because
well, that's good. Unfortunately,
that's the practical application. So that's how I
exactly. But unfortunately, we don't have that part of the textbook, which is getting into that, is towards the end, and we don't, sort of. If it was a year course, we definitely do it.
I just thought it was really interesting that the variance is approximately like for this. This is a completely uniform distribution between 6 discrete possibilities, and the variance is approximately half of the entire size of the distribution. I was wondering if that tends to hold true for uniform distribution.
I don't know enough. I don't know enough to tell you. We can, if you hold that thought, when we do continuous random variables, then we can nail it down. Okay, so what we needed here was the linearity of the expectation, and this is a hard nut to crack. But because I've got math majors, I cannot avoid this. Okay, I can't. I hate proving things in this class. I'd rather just do problems, so you get this intuition. But I have to, I have to prove something, and this is the most critical thing: is the linearity of the expectation. This is what it's based on. So proposition 4.1. The first major thing, theoretical thing. So this is saying that the expectation of some function of the random variable is this. So you take the different values of the random variable, hit it with g, and you multiply by the probability of that value. So this is. You might say this doesn't make any sense. That's what you expected. Yeah, we expect it to be this. But what's different? What is different about this? Normally, with an expectation, you would take it would be the values of this. This would be your new random variable right here. Normally, I hate to use an x here, but you won't get it if I do. So normally, it's that whole thing, whatever its values are, and then it wouldn't be x. It would be y. Y is the values of g of x. You understand? This is actually something to be proven here. This is not a given. So let me quickly write down something. And if you're motivated, you can analyze this proof, quote unquote proof, and quiz me about it later or in office hours or something like that. So to prove it, you look at the right-hand side, RHS, which is this, and you can rewrite that. It's just like I'm saying. So I'm going to look now at the different results of g of xi, and those are finite, and or countable, but let's assume things are finite. And then we can refer to those as y sub j's. Those are the different values of g sub xi. As x, goes through its different values. So we can write this as y sub j, and we could collect all of the i's. This is I such that g of xi is y sub j. We can collect those i's that correspond upon application of g to this one of the finite values of g of x. So this is P of xi. It's just from right here. In other words, we're breaking this down into pieces. Okay, and the theorem's almost done because this is y sub j times what? What's the probability? This is the probability that g of x equals y sub j. Why is that? Well, because you've collected all the xi's that when you hit it with g, you get this particular y sub j here. This is a j. Okay, and this quantity right here, this is the expectation of g of x. Okay, why is it? That's by definition. These are the different values of g of x, and this is the probability that it takes on that value. Okay, so that's that. You can write that down, or you can look in the book for a more confusing version of it. So, what is the corollary here? Because I really want to get. What do I really want? What am I hunting for? I want this. I want this as a e of x plus b. I really want that, and I don't see that in this right here. So obviously we've got to consider that g of x is equal to this. Okay, let me just check the. Okay, so let's. I'm sorry I have to erase this so suddenly, but everything that's important is there, and what is not important is not there. So what I wrote here is a lot shorter than what's in the book, but I don't like what's in the book. P of g of x equals yes. No, this is the probability that g of x is y sub j. That's one of its values. That's one of the values of g of x. Okay, because we've collected all these ones, these individual ones. These are all the x of i's that are when you hit it with g of x I, you get the y sub j. So you're combining these probabilities. So you get the total mass that corresponds to g of x being equal to y sub j.
Oh yeah, so basically we're using another variable here. We're looking at it in terms of the expectation value of y. So
well, yeah, but the variable is actually g of. Okay, that's good, but it's actually this is bad notation. But g of this is the variable we're looking at, g of x.
Right.
But you want to make that a y, yeah. And maybe I should have done this, but I thought it would confuse people. So this is the new random variable.
Well, you're yeah. So that's what I'm saying. Your right hand side is showing there that you've got the expectation value of y basically. So
Yes, right. That's exactly what this is.
Now we want to show that. Now what we're trying to show is that is the same thing as if we were. You want to show that basically, that with that.
Okay, we got to be careful. We got to be sort of careful here. We got to be a little careful because if the right hand side is what you said, this would have to be the probability that y equals or you see this is not e of y, right, as it is. E of y would be this times the probability that g of xi equals g of x equals yj. You need this. This is not okay. What I'm trying to say is this has been broken down. See here, this is on I, this is on j. So this is not exactly the same as this. You have to do these other steps. Okay, but let me move ahead to the linearity. So this is a corollary. This thing right here is going to be a corollary.
What does the word corollary mean exactly?
That's okay. I'm a math person, so you're going to get if you have a big result, we call it a theorem. If you have a little result, most people call that a lemma. If you have three smaller results, does anybody know what the plural of lemma is? A corollary is usually when you have a theorem is this big thing here, and then it has implications. And sometimes the implications are smaller things, but they rely on the theorem to prove them. They're usually called corollaries. So they're sort of swift implications of the bigger theorem.
Oh, I see.
If your theorem is super large, you call it the fundamental theorem.
Okay.
Like you've already
corollaries can be like tools that we use the theory?
Well, you could probably come up. I haven't taught calculus forever, but I mean the fundamental theorem of calculus 1, right? I mean, or 2. Can you think of a corollary to that? It's been forever since I taught that. You know, think about it. Let's just keep that in your mind. I'm already spread between 2 classes.
Would that be kind of like U
I did.
substitution for would be like a corollary of the fundamental theorem or
Okay,
something?
but just for the joke, I did once when I had a lot more hair and I was younger, teach calculus. And I remember somebody, the U substitution, they started it, let U equal X.
Say that again?
They said, let U equal X.
Oh.
Okay, good.
That's so useful.
Right. And
Get a nicer looking variable.
Come on, you guys. Let's have some. Just tell me. What's the plural of lemma? No, probably of
lemons.
Well, close. What is it? Okay. While you're pondering that interesting thing about the English language, let's try to get this corollary. So I'm trying to prove this. And so let's put an arrow there to what we're trying to do. So how do we do this? So E of AX plus B, what am I going to do now? Well, what did we just do with the theorem? The theorem said if you have a function of the random variable, so this would be your G of X, they said what? This is equal to what? Over all the different values of X. So this is G of Xi times the mass function of Xi. Okay, that's the theorem. This is by theorem 4.1, and nobody has told me the plural of lemma.
Is it lemma? That's in the chat.
That sounds like a lemniscate. Isn't that some sort of trigonometric curve or something? Some people are angry now. They just turned off their video. It's okay. I'm sorry, you guys. Just you have to get used to my personality. I'm sorry. Okay, so what is this here? So G of X. So what is G of X now? It's AXI plus B times P of XI. So all we need to do is multiply this here, and we get, this is now A. If you have a summation, the A can come out. And so I have Xi times P of Xi from the first, we're going to break this in sum into 2 parts. And the other part is, this is the thing you might miss if you're reading really quickly. So look at the second part. This is B, a constant number, times a bunch of probabilities. But you see, if you add up all the probabilities of all the outcomes, you must get 1. Okay, that's definition. So this part right here is B, and this part right here is what? It's A. This is the same as the expectation of X. Okay, now you might say there's been a lot of shouting, nothing's happened. Well, no, this all relied on theorem 4.1. You have a sum, and you're going to add things up in a different way. So it's like the Fubini theorem from calculus.
So, wait, what did you just show again?
We just showed this. And I needed this result.
Or
I needed this result to do the calculation with the variance.
Okay, so you just took it's basically a linear function.
E is, I just proved the linearity of E. So it goes into here, so it distributes into the sum.
Okay. So does this basically prove that does this imply that, I mean, it looks like it implies that for any linear function, you can do that thing?
Well, it's a linear, it's, okay, from 220, was it 262? It's a linear operator, the E. It's what we're saying now. And you guys have used this, and I think you even have used it on the test, the first test and the second test. Where do we use this stuff? Do you remember you had this balls and bins problem, and Xi was what? Xi was 1, if bin I was what? Was empty? And 0 otherwise. Okay, and what do we have? Didn't we have like a sum of these guys? You guys remember this, right? On the test? I don't know, the first test, second test. Right? And what did we do? We took the E of this. What I'm doing is does it ring a bell? Yes or no, right? There was some problem about how many, what's the expected number of empty bins, right? The expected number of empty bins. And so what's your very next step? You're going to distribute that, right? We did this, right? So what I'm doing now is giving you some justification for that operation. I gave it to you first. I gave you this technique first so you'd be comfortable with it, okay? So you could see the power of it. But there was no justification that I never proved that the expectation had that, the properties of a linear.
I never noticed that that was a linearity thing.
That's critical because that's how you do all of the problems.
Okay, well, I get it now.
If you there's so many problems like on the final 2 and the next test, on this test and the midterm 2, aren't there problems where you've got to take expectations, right? And so it's good to know that that's linear. I mean, it makes some of these problems doable.
So basically, the linearity, this corollary or whatever, is so this is like a result of that theorem that that you can get the g of x thing. Basically, you take a function and you can sum up the probabilities based on the input, not just the output. I mean, that was theorem 4.1, right?
Oh, I don't know about the it sounds philosophical what you're saying. It's just
I think
262, right? Linear algebra. We're just showing that it's a linear operator.
Oh, okay. Well, just
a lot of times guys will ask me, they'll say, okay, what about this? Is that does it distribute this way? Okay, a lot of guys will ask me this at this point, and I'm telling you, it doesn't usually do it unless those 2 random variables are so-called independent. Okay, so it doesn't do it. It doesn't. It's general no. You can't do it for a product. Well, that's expecting. There's no miracles. Okay, let's do something else really quick. Since we're on this proofy kind of. But you guys understand this, right? This was critical to solving that problem with, was it 4 balls going to 4 bins? How many empty bins do you expect to end up with? Okay, this was critical, right? But I want you to realize, we have not proven that this was a legal step here. I just wanted to give you the technique so you can carry it with you for a large part of the class. Okay, so let's look at variance one more time and we'll go into something else. In fact, I'm running a little slow here, so let me just check the box off. So variance of ax plus b. What do we expect this to be? Well, for one thing, the b, if you're just translating your verb, so if I had a normal curve here and then I translated it over here, okay. Well, relative to its center, it's got the same thing happening here, right? So the translation of all your data is not going to change the distances to the mean, okay, or the square of the distances to the mean. So the b is not a factor, but this a, it turns out when it pulls out, it becomes an a squared. And again, that's not terribly surprising because the definition of variance involves the square of x minus the mean, right? The square. So you expect things to increase. I'm a computer guy, right? So I teach algorithms, and so variance. We already had an example of that. The variance seems to, when things get spread out, it increases quadratically. Now I have
increases what? I'm sorry, my house is all of a sudden very noisy.
Quadratically. Maybe I should do this thing. I'm sorry, I have to use notes here. It's a little bit tricky, this step. Let me tell you where it's tricky so that you can review this when you get home. I don't know if I'll do the whole thing, but we have to go now to. So what should I do at this point? I want to prove this statement. And I'm looking at variance of var of ax plus b. What do you think I should do? What would be the first? If you're a math person, what do you think I should do?
Write down the definition of variance, or we could probably use the one that we found earlier with expected value of x squared minus expected value of x
Right.
squared.
That's exactly the wrong thing. It turns out.
Oh, really?
That's what I did when I was doing it at home. I did what you said, all right? Because that's, as a mathematician, you want to use the tool you just developed, right? But it turns out in this case, it's way better to go back to the original, like you were saying, the original definition of variance. Right?
Okay.
It's strangely.
Sure. Go ahead.
But again, I did the same thing you did. I said, what's our latest best tool? Let me use it. And I found out I got a big zero out of that. So if you go back to the definition, hopefully I can get this right. What is the definition? It's the variable. What is the definition of variance? So E of y is what? Equals expectation of y minus its mean squared, right? So in this case, it would be ax plus b minus the mean of this. We already know the mean is from last time. What's the mean of this thing? Minus the mean of this guy is a mu minus b. Okay, but the thing is, I got to square that. So let me put the parentheses in there. Okay, so let's do a little. So again, we're going right back to the definition. We're not doing the fancy corollary. We're not using the corollary of. So again, what do I do here? Well, just a little math. What is this? This is a x minus mu, and you're supposed to square that. And so what do we get here? So this is e of a squared. A squared what? So a squared times x minus mu squared. Okay. So what do we know about expectation? It's linear. So that a squared can pop out. This can pop out, and I have e then of what remains. X minus mu squared, right? But this is the definition. You see, this is where it would have been bad if we went the other way. I'm just going to report what that is. E of x minus mu quantity squared, that's the definition of the variance. So that's a squared var x. Let me check the time here. Time is actually pretty good. There's an interesting problem involving the binomial distribution.
Okay. For what it's worth, I did do it with the new definition, and I still got it to work. Just for it does work.
How much? Which was easier?
I got it in 4 lines. You got yours in 4 lines. So
I wonder why I was failing to do it.
I mean, at the very last step, I have a squared times expected value of x squared minus a squared times, and just being very careful with parentheses, the expected value of x squared.
That's correct.
So yeah, it does. Perhaps just it looks like those are the same. You cross them out, but they're not. So you can pull out the a squared, and you get what we have for variance.
Well, I have to be honest with you. I wasn't successful.
Oh, okay.
When I did it,
it does work.
Yeah,
I don't know. Either one works.
It's good to know, but I like this idea that it reduces to something we already, we can just pop that.
Yeah, absolutely.
But okay, that's good to know. I don't know what happened to me when it didn't work out. It's just that's life, right? Okay. Let me be a little bit ambitious. Let me try to give the first really interesting thing in this chapter. Let me see if I can get it across. It's not about variance. It's about the binomial distribution. Okay, so this has got everything in it. So what example is this? 6F. Okay, if I can get through this, I deserve lunch. Okay, 6F. Totally washed out. So that's the harbinger, right? Okay, so there are two machines, and they have identical components in them. And each one will work if more than half of the components are functioning, but they're all independent and they have the same probability of working. So let's draw a picture to try to understand this, what the situation is. So one machine has 5 components, it's 5 of these things, and another machine has 3 of these things. And when I say things, those components are identical. They have the same probability P of functioning. Okay? And this is the big step. I'm telling you that this, being honest with you, I can't do variance, but I do know something interesting. That this binomial distribution, these problems, some of them are very clever. Okay? It's very, very, very interesting. This is one of them. The application of the binomial distribution. What is the binomial distribution anyhow? So this is how they write it in CLRS. They say X is binomial NP, which means what? This means that you're counting the number of successes in N trials, where each trial is independent of the others, and the probability of success is P. So the P stays the same for all the trials. And we've done this, we've looked at this situation with tossing a coin, maybe you call it success heads, and failure tails, and stuff like that. And it has a distribution. What is the distribution? What is the distribution? The probability of getting exactly I successes in N trials, what is that equal to?
I don't even know what function is causing X in the first place.
Okay. Let's do some tails and heads stuff. Suppose that N is 5, right? Okay, and your outcome is, you're looking at this outcome. Tail, tail, head, tail, right? So X evaluated on this, what's it going to return? This is an outcome, right? This string here of tails and heads, but it's counting, this guy here is counting the number of heads. So what does it return? Is that good? This random variable, it's this function. Your sample space has these sequences of 5 results, with tails and heads, right? But what you want is the number of heads. Okay. So what if it's all tails? What is this function here? 0, right? I kind of assuming you knew this or some people knew this by working on the Roy and Slid problem. Is this a stretch, or you guys? Did you do the Roy and Slid problem already on the test? Please don't tell me you checked it. I know you didn't check it. Not this class. The late one, yes. Okay. Are we good?
I mean, I'm pretty sure I know the binomial off the top of my head. It's n choose I times p to the I times 1 minus p to the n minus I. I think.
Let's write that down. Okay, can you say that again, Amy?
P to the I.
P is the success probability.
Yes, probability of success times 1 minus p to the n minus I.
Very good.
I think.
Okay. This is the mass function for it, but I'm telling you, it's very intuitive if you think of successes and failures. Okay, it's just going to count the. Oh, wait a second. Okay. I can't believe somebody's calling me knowing that I'm teaching. It's like, I can't believe this. Okay. Anyhow, so this is very intuitive here, okay? Because if you have a string, say I have 20, a string of 20, right? And you want to know what's the probability of getting 5 heads in there and the rest tails. There's lots of ways that those 5 heads could occur, right? And that's why you have 20 choose 5 to figure that out. So let me see if you guys get this. This is not in our textbook, and I'm surprised. Just listen to me carefully and imagine this situation. You're in a small town, okay? You live in a small town, and there's going to be an election for some position. And there's 100, or say 1,000 people in the town, okay? There's 1,000 people. However, nobody cares about this election, but they want to vote. So everybody just votes for one or the other. Okay, there's 1,000 people. So 1,000 people, they're going to vote and it's one or the other, okay? 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 So what would be a strange outcome to this election? Remember, it's
It'd
50.
be strange if it weren't like very close to 50-50.
Okay, that's very good. I didn't expect that answer. Okay, now again, don't do any calculation. How likely do you think it is that it's a direct tie? If it's a direct tie, then the outcome is it hasn't been decided who wins. And people are sometimes surprised to see that for a tight election that you could actually get a dead heat. What do you call that? Exactly the same. 500 in one and 500 in the other. So could you please tell me, based on what we have here, what would be the probability of getting a 50-50 tie? So 500 people for one candidate, 500 for the other. Could you fill that in for me here? What is P of what? Tell me what it would be. P of what? You're going to have 1,000 votes.
Oh, now I understand why they call it I don't fully understand it, but I can sort of see
This will count. So this
why
is
they call it binomial now.
This is 1,000, and this is going to be what? In this case, what is my probability of a success here?
Wait, what? What's a success?
Okay. Success will be like one candidate, failure will be the other. So it's either one candidate is success, the other is not. So it doesn't matter. So what's the probability for candidate A? Let's call that the success. Probability of candidate A getting the vote is a half, right? So that's our assumption. Okay, so let's calculate this. Maybe somebody's already done it.
I still just have no idea what that is on the screen. On the board.
Okay. So,
Any of that.
Okay, so you have this is the binomial random variable. So this will count the number of the probability of it will count the number of successes in n trials. So a trial is either up or down, yes or no, true or false, candidate A or candidate B. There's just 2 outcomes, okay? And this P is the probability of the success outcome, okay? So, okay, before we calculate, does somebody want to just blurt it out? What was the probability we got?
I put it in a calculator. It's 2.5%.
Amazing, right? Tell me that. Is that amazing or not? Amazing.
That's a very large, chance. That's interesting.
Yes.
Like out of 1,000 people to have it exactly.
If it was
500, that's great.
Some elections. If you remember Kerry versus Bush, right? Florida. You guys were too young to remember it, but anyhow, that was really tight. There were some counties where it was essentially 50-50, and people don't understand that. Nowadays, the way things are going, people would say that can't be. It's a hoax. You can't get 50-50. Well, wait a second now. If it's really
that's so funny, it is actually more likely than other outcomes, isn't it?
Oh, I don't know about that. But the thing is, it turns out that we're talking about P of 500 is 2.5%, right around that. Okay, people don't understand, but this is the justification. Why is it so large? Because there's lots of ways that it could go 50-50, right? I mean, there's a lot of people, you got 1,000 people, right? For it to go 50-50 a particular way will never happen in the universe's remaining lifespan. However, to get it some way, if it just hits one of those ways, there's so many ways that it overpowers what? It overpowers, this is a half to the 500. Half to the 500 is an enormous, it's just crazy. It's forget it. But the deal is when you do this whole calculation, you get 2.5%. Okay, so now that we don't understand, no, I'm kidding.
Well, that was actually really interesting. I went from not having a clue of what was going on to actually that was kind of.
Thank you. Just remember me when I'm gone. No, I'm just kidding. Okay, so let's go back to this problem, which is the first sort of deep, semi-profound problem on the binomial distribution. And there's many more coming in the book, but this is the first one. How many of these have to work for this to have more than half the components working? So you need what? You have 5. So how many components have to be functioning here? At least what?
3, 4, or 5.
At least 3. Very good. And here, at least 2. And just as Aim is saying, this means we're talking 3, 4, or 5. And here we're talking 2 or 3. Now we have to stop here. We can't just go zooming ahead. We've got to think, what are they going to ask us? What possible problem could they ask us here? They're going to say, which of these setups, they call them systems, they get, Ross likes those engineering terms. There's system 1, system 2, whatever. But which of these machines is more reliable? It's going to be more reliable. And that's kind of from left field, right? Because how do we measure reliability here? Well, you measure it if it's working. And it's working if you have 3, 4, or 5 of these, what do you call them, submachines or components are functioning. So how would we make it compare? Now, maybe some people, this is not so deep. How would you compare these things? I mean, you want to know what's the probability this guy works? What's the probability that this guy works? What do we need?
We could pick some arbitrary, somewhat large number of trials, I guess, and then.
Well, that's simulation. That's simulation, right?
Well,
that would be a simulation. So we want to do this theoretically. And it's saying that they want you to report your answer in terms of P. So that's telling us that maybe the answer to this question depends on what P is. Okay, so all of a sudden this gets a little bit cloudy, right? There's 3 things going on. You got 2 machines or systems. They have components, identical components in them, but not the same amount. They have this condition, right? And so to get started, we got to say, what is the probability? If I'm going to compare this guy to this, I got to know what's the probability that this guy's working? What's the probability that this system is working? And compare them. They will both be functions of P.
Well, we could do the binomial thingy over one system and then do it over the other system.
What is the probability that this is? So probably that, let's call this A and B. So probably the A is working.
I have a guess, if I can venture a guess, what I think is going to be more reliable.
Let's calculate it. So you have 3. Now we have to know this binomial distribution mass function. So what is it? So if you have 3, what's it going to be? These are 3 cases, so I've got to add 3 cases. So
5 choose 3, right?
Very good, very good. Redeemed yourself. Okay. So 5 choose 3, and now 3 are working, right? So that's P is the probability of one is working. So 1 minus P must be the ones not working squared, plus what? When you have 4, so 5 choose 4. 4. Then 5.
Wait a minute. Wait, what's 1 minus P squared for?
Okay, when you do, you have 5 shots, right? So you're looking, what's the probability that 3 of them are successes? Well, you have 2 that are not. So these are independent. These trials are independent. That's why you have to multiply. Okay, like let me give you. I just suppose that I'm rolling 1 dice, and I want to, and I make 5 rolls, right? I get so what's, it could be asking, what's the probability that I get 2 snake eyes? Okay, two snake eyes in this. Well, how many rolls do I have? 5 altogether, right? Right? And we look at the case of the 2 snake eyes. It can happen that many ways. I think that's 10. And then you see your probability of getting a snake eye is what? 1/6, right? So you calculate that, that's squared, wherever it is. And the probability of not getting a snake eye is 5/6. And how many? There's 3. So this covers all the possible ways I could get 2 snake eyes and the rest not.
Okay, so wait, 1/6 squared is probability of getting snake eyes, right?
Two of them. These are independent. So you hit this and you hit this. What's the probability of this? And then having this happen. And you got to multiply them because they're
Okay, well, I guess when I say snake eyes, I mean 2 ones.
Oh, no, we're talking about one roll. It's a snake eye, but there's 2 of them. So I'm sorry about the confusion. It's, I don't know how to say it. Snake eyes. Okay. Please don't record what's going on.
And then the 5/6 to the 5/6 to the third is
getting
the
these
number of what is
okay, these are the non-snake eye rolls, and so but the probability is 5/6, right? That we avoid a snake eye in there.
Okay, so that's so that we avoid a snake eye.
Right. So this is this is the probability of getting 2 snake eyes, single snake eyes, and exactly 2.
Well, that's counting the number of ways it can happen, right? So what would the sample space be for that?
That's a good question. It would be the sample space would be the sequence.
6 to the power of 5?
Yeah. It's the sequence, these sequences.
Okay.
And you can put numbers for these sequences you want. 1, 1, 3, 3, 4. It could be anything. But I just wanted that it's been taken into account.
Whenever we use combinations in sequences, I get kind of confused between going back and forth between the 2.
I'm almost out of time, so let me get the other one, and then I'll send you guys home with this problem. What's the other one? Help me out here. What's the probability that B works? What's the probability that die works? Very low. But what is the probability that B works? What do you have here?
3 choose 2 times p to the 2 times 1 minus p.
Very good. And what's the other one?
Plus p cubed.
Right. Okay. Now, that question was, for what p is this doing better than this? So how do I want to compare these two? Assume p is fixed. We want to know that when this expression probably is higher than this. So you need to put I don't know if you can do that in your paper, that this thing is greater than this. I'd like to know for which p that I have this relationship.
So it does change based on p?
It certainly does. But you see, you guys have some work here, and I'm out of time, so I can't help you with this. But you have to do, believe it or not, I mean, this is Ross for you. He's an old school kind of guy. So what do you think he's going to do to you when you do this? He's going to see if you remember your algebra and how to group things without making a mistake. And in particular, how to factor, because you're going to get a cubic, and you've got to factor that.
Oh, great.
The game's going like this.
No one likes factoring. If it's more than a square, we always first we cry, and then we go ahead and try to do the thing.
Okay, well, you're going to be a teacher, and you're going to, maybe, or a professor or something like this.
I hope
you should
so.
teach that method. First we cry.
I say it. I'm not even kidding. Whenever I see it, whenever I'm working with my high school students, is whenever a cubic shows up or anything higher. First we cry, and then we start, using all the tools that we have.
Okay, but look. Brandon's saying, what are we solving for? You're trying to find for which values of p is this machine, this system doing better than this system in reliability wise. In other words, but then we've got that down to, I want to know when is this bigger than this for which values of p. So I've got to do some simplification. Now let me, before we end, you got a cubic. What is the real technique for solving a cubic? Practical, when it's you and a pencil and paper, and you got a pad pencil and you got a pad of paper. What do we all do to get started? If you can knock it down, yes, right. You want to knock it down to a quadratic, so you look for a root, and then you use synthetic division to divide out that x minus whatever that root is, right? So what would be
Or
the
we put it into a calculator
no.
that can do
Ross
that.
he didn't do
Because
this.
that exists now.
Ross didn't do all this for somebody just to punch into a calculator. You got to, he didn't do that in there. He didn't say, how can the B be what? How can the B1 be 2.5? I don't know. Well, that's a 3, 2 or 3. Okay, this means this guy will be working if you have 2 of them working or 3 of them working. That's more than half, right? You got 3 things, right? If you have 2 of them going, you've got more than half, right? You got 3 of them, you got all of them, right? Does that make sense? Brandon, are you good with that? Okay. This was a notation. I was just saying if you have at least 2 of 3 things, you're talking about you either have 2 things or 3 things. Okay. Okay. I think I'm out of time. Could I ask you guys to take a little excursion if you have any free time and try to solve this without looking at the book? And if you're anything like me, I find that this is extremely challenging to simplify this correctly. I don't know why. I don't know why the problem is. Maybe we don't practice this in school, or I don't practice this skill. There's a skill here. And knowing that I've had trouble doing it myself, could you do it really carefully and see if you can get it on the first pop? Find out what the answer is. It's just amazing. When you do all the simplification, it's amazing how easy it is to make a mistake. I think we learned something about ourselves. We learned about our own reliability.
And can I take I'm gonna take a screenshot real quick.
Okay.
Cheat.
I think I'm done with this today. I'm sorry we didn't cover so much, but on our test,
Don't worry, it was difficult enough to understand.
Well, I'm trying to think of the test. I didn't really. I mean, Roy and Slim is a binomial distribution problem. So hopefully what I did today will help you nail that one off correctly. Any other issues with the exam? I mean, I'm trying to.
Professor, would you be able to take a look at number 3, the one about the diagram for Ross?
Yeah. Can I erase? Let's just make sure I can erase this. Let me check the chat. Does anybody have a question about this?
I'm good on it now.
Okay. Anybody else? How many people are with me here? Because we're over. Let me we got pretty good. We got 20 people. That's good. Okay, so you guys want to look at. So this is your homework to do this, and do it trying to be careful with your algebra. Okay, just. If it helps, think of me not getting the right answer, maybe because I'm rushing. I don't know what it is. I'm just not able. It's like playing a piece on the piano. How many wrong notes are you going to hit? And I've never been able to do a hard piece without making wrong notes. But I know that there's people who always hit the right note. I don't know how it is, but they do it. Okay, so we're talking number 3. It's the circuit problem, right?
Yes.
Okay, so let me draw that real quick. I'm getting good at drawing this because we've done it so many times, right? So this I can do, I think. Oh my gosh, am I going to make it? So this is a knot, right?
Yeah, the third one.
Okay, and coming out here. Okay, so I guess this is B and A. So we have line in, right? So there's power coming in, and you want to know what the probability is that you're going to have power coming out. So there's line in. There's no question. It's not like, you got power coming in with probability 70%. No. You got line in. Okay, everybody knows that from messing with their stereo system. So there's line in, and then what happens here? Well, if let's give some numbers to these. 1, 2. What did I call this one on the test? 4 and 5.
That one's 4, 5, and then the middle one was 3.
So with what probability are these gates closed, these relays?
1/2.
Right. That actually makes it easier for you guys. So Aim's still there. Let me ask, because she may have... Aim, did you look at this one, or just curious, or is this later on for somebody else?
I mean, I've looked at all of them, but I was planning on putting more time in during the weekend. It's been a very difficult week for me.
It's been a difficult
So-
week for me too. What's with this
Yeah.
last week? It's just kill it. Just
Well, I didn't have spring break because I had my jury duty.
you really
so-
didn't. You didn't say. You didn't say membership has its own rewards or anything like that.
Yeah, no, I did get on. It was just, someone traffic accident and deciding how things get paid out and all that. So that was fun.
Yeah,
But yeah, and then I had my COVID shot and now I'm sick. So I'm just kind of like, ugh. I'm hoping I'll be feeling better enough by the weekend to really dig into this test.
Our vice chair said that she was sick, couldn't do anything for two days because of the second COVID shot.
Basically, yeah, that's kind of how I'm feeling right now. So my head feels like mush.
Oh my gosh! I'm really, really scared about the second shot. Not. Well, let's see if I can do anything here that might help you understand this problem. So, if you had one open, say no power coming in on one, then you would definitely have power emanating from this logical knot here. Is that true?
Well, not
Now, if
exactly.
these two are closed, you might be going like this, but you wouldn't need it. It wouldn't affect this power coming through here. So, yeah, if you had 2, 5, and 4 closed, then there'd be nothing coming out of here. But if these are closed, you're going through. So you've got to figure out all the different possibilities.
Sorry. So if there's no current going through one, then the middle one is powered?
Yeah. Well.
Well, no.
Okay. If you have power coming in, okay, to this, you're not going to have anything coming out.
That would be so. One would have to be closed in that situation.
Unfortunately, no.
Wait, what is that thing in the middle?
It's an inverter. So if you have power coming in, then nothing comes out.
Oh, I
If
thought it
nothing
was.
comes in, then
Oh, I
it's
thought that was just another switch.
No.
Because this is a different problem, then, isn't it?
Logical
Another
knot.
one.
It's,
Okay.
I think it may be called an inverter. I don't know. I'm ignorant about these things, but it's going to reverse. If you have current coming in, then you'll have nothing coming out. If you have no
Right.
current coming in, then you have current coming out. So we just
Right.
noticed that if this is closed, and this is closed, then no power will come out of this. But that doesn't affect our outcome because we have power this way. See. Remember, the outcome is: do you have power coming out of B or not?
Yeah.
Let me just ask. Curiosity killed the cat. We still got 15 people, which is pretty wild for this late in the hour. How many people did this already in there? I'm talking to 15 people. And don't tell me how you did it. I just want to know. That's a dumb question on my part, right? Because it's just like that's a dead cat.
It looks like no.
Well, it
I
looks
know
like a
it's
dead
no
cat.
for me. It's just timing wise hasn't been great.
Does this help at all? This observation that
With the inverter, that's kind of cool because you could have 1 and 2 both open, and just 5 closed, and then that would complete the circuit.
exactly right. I don't want to tell you.
But doesn't
Go ahead.
doesn't it have to flow from A to B?
Yes.
So
Well,
No, it doesn't have to. No. You just have. Okay, great question. No, it's just a question of I guess the saying closed is the wrong thing. Closed means in electrician parlance, it just means that there's power coming out. So that's an excellent question. No, we just want to know what's the probability that you see power at B, given that you have power coming in at A.
okay.
Sorry about that. Yeah, no, you bet. It's the electricians. They'll say it's a closed circuit. I think I'm wrong here. That it just if something's coming out of it. I think that's how they talk about this. I could be wrong, but right. So I may have to rewrite the verbiage on the
that's an
test.
interesting technicality.
Yeah, because I was looking at it. I'm like, there's no situation where the power would flow through the inverter at all.
Right. You're right. Okay, I'm sorry. I didn't think of that when I was writing the problem. So,
So it's just
I want to
question
know what
whether
the
B
probability.
gets power or not.
Yes, I want to know the probability of B. Where B, I guess B will be the event that there's power here on the output.
And then you don't mention independence. The original problem has independence. I'm guessing it doesn't matter. We're just assuming that it's independent anyways.
These are independent.
I would think independent.
Those are independent, and they all have the same probability of being closed. So that should help you guys when you
Yeah, that makes sense.
when your group starts to sit down and look at this in earnest. There is a pretty simple way to resolve it. The problem.
All right, I
Go-
gotta
gotta
go.
go.
Thank you, Professor.
Thank you, Professor.
All right, you guys. Okay. Any other quick question? Because I've got a bunch of I've got committee work phone calls coming in on me. Bye, Edwin.
For the question 11 about the businessmen
Let me
and
check
two
that.
restaurants.
Let me grab it. Well, I can't find it. Hold on. Problem 11. Yeah. Okay. So he needs two bad years. Let's see. He needs 3 bad years, right, to die out, to lose the business.
For business, restaurant 8, yeah.
Oh, are you doing the first? Or are there 2 parts, or well, he has 2 restaurants.
So there's 2 restaurants,
Yeah.
and then we have to find out which one is expected to stay in business longer.
Right. Did you do the first one where it's just?
Yeah,
2 bad
yeah.
years?
I think the first one was pretty similar to what we did in class.
Yes.
And I
yes.
think I found the second one, but I came to pretty close numbers.
Right. When I can't reveal,
Yeah, yeah.
However, I think this is simple, right? You could write a quick simulation, right, and then see if you got the right answer. And I think after 50,000 reps, it's in the blink of an eye, your computer will tell you if you got it or not. Just do it 50,000 times, and then just calculate how many of those you're still in business. You the length of time it takes, the number of years before you go out of business, and then just average up all those, and it'll be really close. So that way you'll know that your theoretical answer is correct.
Okay. All right. Yeah, because the numbers were just pretty similar. So I was like, I'm not sure if I should round to whole numbers.
Yeah. No, I would do this simulation, because you never know. Maybe there's something wrong with the way we're approaching it.
Mm-hmm.
Tree. I doubt it, because the other one I've seen something. The other one I've seen somebody do it with Markov chains and software. It comes out exactly what we get with my method.
Mm-hmm. Yeah, because I used the trees. So
yeah. Well, that's a computer science kind of approach, I think.
Yeah. Okay.
But it's definitely simulation.
Just going back to the triplicate problem. So it's okay if we use So I used the Poisson approximation to get close to.
That was to get the idea, but then you still have to prove. You have to prove what is that probability you're looking at. When you decided, say just for the sake of argument, suppose your answer was 9. Say, okay, then you would have to get